Let's look at work. So we looked at heat transfer now, right? What is work? Work, energy associated with a force acting through a distance. So if energy crossing a boundary is not, this should be heat, not here. If energy crossing a boundary is not heat, it must be work. That's what's great about the first law, because energy transfer can only take place over a few different ways. Notation associated with work, again, W12 is work between states 1 and 2. This should be little w, right? Little w is big W per mass. And then work rate, work dot is power, work in transit. So this would be, again, in watts or kilowatts if we're working in SI units. What about the direction of heat and work, right? How do we, when we look at a system, when we're analyzing a system on a first law analysis, how do we discern whether work and heat are positive or negative quantities? Because they are directional quantities. So a complete description of heat and work interactions requires the specification of both its magnitude and also direction. So here in thermodynamics is the formal sign convention. I'm going to cover this, but you can look at it differently. I'll explain what I mean. Heat transfer to a system and work done by a system are positive. So here's my system boundary. Here's my arbitrary system inside that boundary. If I have heat leaving the system, it's considered negative. If I have heat entering the system, it's considered positive. If I have work entering the system, it's considered negative. If I have work leaving the system, it's considered positive. And my understanding is basically that means that when we're looking at work, a system is trying, we're looking at thermodynamic devices, which are basically trying cycles or processes or cycles with which work occurs. So the work coming out of a system is considered positive because most of the time that's what you're looking for it to do, is produce work or convert energy from one form to work. You could count it as positive going in and negative coming out as well. It doesn't really matter as long as you pick a system and you're consistent with it. An alternate sign convention would be just to use subscripts instead, right? So if I have Q going into the system, I call it Q in. If I have work going into a system, I call it work in. If I have Q going out of a system, I call it Q out. If I have work coming out of a system, I call it work out. So if I look at the relationships between the sign conventions, I would get work, total work of the system would be work out minus work in, and the total Q done on or by a system is Q in minus Q out. So here are some characteristics of heat and work. A quantity that is transferred to or from a system during a process is not a property, since the amount of such a quantity depends on more than just the state of the system. All right. Well, I know when I go over this in my classes, that sentence tends to be a little beefy. What it's basically saying is that heat and work is not just enough to know the state change of the system, right? If I have a system that's going from state 1 to state 2, I need to know more than just the state change, right? It's kind of like going back to that scenario. Here I have a room, and here I have an object, a desk in a room. I move it from state 1 to state 2, and that distance is 5 meters. Can I figure out how much work it took to move it from state 1 to state 2? And the answer is, well, I need to know more than just a position. I need to know how it happened, right? Did I drag the desk or the object all the way across the room to here, or did I do a direct line from point 1 to point 2? This obviously requires more work than this does. So it's the same thing. Heat and work are quantities that happen because a process happened. And so I need to know both the state change and also the path or the way it happened. So heat and work are energy transfer mechanisms between a system and its surroundings. So both of them are boundary phenomenon What does that mean, boundary phenomena? It means that I only recognize always, under all circumstances, work and heat are recognized at the boundary. If I have no work or heat crossing a boundary, no work or heat transfer is occurring, period, for that process. And their path functions. Path functions means it's not just enough to know the state change between state one and two. I need to know how it occurred, right? We talked about the other difference. If I have a pressure volume graph, which we're going to look at a lot, state one, state two, those are the two states that occurred, right? I went from this point to that point, this pressure and volume to that pressure and volume. But the path that it takes, how I get from one to two, the type of process that occurs, that results in different areas under this curve, right? The area under the curve is representation of the work, which can be quantified as the integral of PDV. We're going to cover that in a little while. But my point is that it's not just enough to know the state change between one and two. I have to know how the process occurred so I can define the path of the process. So this is actually from your books, and I thought this is a really good comparison. It kind of looks at the type of functions and the differences between path functions and state functions. State functions, they depend on the state only and not how the system reaches the state, right? So for example, volume change, right? If I go back to this example here, this state here, I have volume 1. This state here, I have volume 2. If I take the difference between volume 2 and volume 1, I get the delta volume. Delta volume equals the volume of state 2 minus the volume of state 1. I don't care how the process occurred. I could have a million times more work in one process compared to another, but the result is the same. The change in volume is the change in volume, no matter how the process occurred. That's called a state-dependent function. But a path-dependent function is different, right? Their magnitude depends on the path followed during a process, as well as the initial final state. So I need to know where it started and where it ended, state 1, state 2, and then I need to also know how the process occurred. That gives me path-dependent functions. And examples of that is heat, work, and overall distance. State functions would be like volume change, or pressure, or internal energy change, or displacement. All right. Let's illustrate this point a little bit more. Again, this is sort of illustrating what I just went over, but I believe that sometimes repetition is the key to understanding something. All right, reading the first bullet point, we have the volume change during a process from state 1 to 2 is always the volume at state 2 minus the volume at state 1, regardless of the path followed. Delta volume equals V2 minus V1, always and forever. In contrast, the total work obtained by following the process path and adding the differential amounts of work done along the path is how you can find the work, right? State 1, volumes at 2 meters cubed. State 2, the volumes at 5 meters cubed. Delta volume equals volume 2 minus volume 1, which is 5 minus 2 equals 3 meters cubed, period. But guess what? Process one process for that to occur follows this path, and the other process for the same state change to occur follows that path, right? My work for path A is not equal to path B. So again, there's no such thing as delta W. There's no such thing as work at state 1 and work at state 2. It is the work that occurred in order for the state change from state 1 to state 2 to occur. So the better designation is work 1, 2, not delta W equaling W2 minus W1. That is false, because there is no work at state 1, there is no work at state 2. It was the work that it took in order to change it from state 1 to state 2. All right. I want to look at some examples here of energy transfer by work. But before we get there, I want to look at some examples here. All right, so let's say I have a room, and that room is perfectly insulated. And I have a candle burning inside that room. And my boundary is the walls of the room. All right, so again, a candle is burning in a well-insulated room. We're going to take the room, which is the air plus the candle, as the system. Determine if there is any heat transfer during this burning process, right? Is there any heat transfer during this heat process? Think about it. I had mentioned that heat is only recognized at the boundary and always only recognized at the boundary. So since it's insulated, there is no heat transfer. Therefore, nothing is happening. Is there any internal energy change of the system? Well, this system is stationary, right? So again, if I go back to what I designate as my first law analysis, there's no energy crossing the boundary in the form of heat and work, and it's a closed system. So energy in, energy out are zero. Delta E equals 0, where delta E is equal to, oops, excuse me, I should have put a plus instead of a minus there. The change of energy of the system is going to be the kinetic potential and internal energy change. Well, system stationary, it's a room. Potential and kinetic go away. So that means that the internal energy change of the system is also 0. And so it's interesting because I get some people and I'm like, well, Dr. Vardy, the air inside of the room is heating up. Or I should rephrase that, not use the word heat because no heat's crossing the boundary. The temperature of the room is increasing because the candle's burning. Well, as we would get later in thermal, what we would say is that the internal energy of the candle is decreasing because the mass of the candle is decreasing, resulting in a chemical change of energy to heat, right? Leaving the candle, like entering the room. So I would have that the change in internal energy of the air in the room is equal to the change of internal energy of the candle. But we're going to cover that a little bit later, right? The point of what I'm looking at right now is that the energy and the internal energy of the room is not changing because there's no energy crossing the boundaries. Let's look at another example here. Let's say I have an electric oven, okay? I have an electric oven. This is the inside of electric oven is the boundary. And here I have a heating element, right? So how does that heating element work? A heating element works because I have electrical energy coming into the heating element, and then the heating element is increasing in temperature, giving off heat from itself to the air inside the electric oven. So let's say I have a well-insulated electric oven, and it's being heated by a heating element. It is to be determined whether this is a heat or work interaction, right? So I have some form of energy crossing the boundary here going into the electric oven. And in this case, it is really important to understand where you are defining your boundary of the system. The boundary of the system is inside the electric oven, including also the heating element. So in this case, I have no heat transfer occurring, right? And this is confusing because it's like, how is there no heat transfer occurring? Because the heating element is making the air inside the electric oven increase. And the word of the object, it's called a heating element. Therefore, heating is occurring, therefore heat transfer is occurring. No, what's happening is that electrical energy is crossing the boundary into the heating element from outside the system, because the heating element is inside the system. And then inside the system, that electric work is being converted, making the element increase in temperature, which is causing the air inside of the electric oven to increase. All that's happening inside the system. I don't care what's happening inside the system. I don't care at all what's going on inside the system. I only care what's crossing the boundary. And what I can see is that electric work is crossing the boundary. So if I go back to my first law, right, E in minus E out equals delta E system, I have no energy going out, but I have electric energy going in. My system is stationary, so there's no change in electric or kinetic and potential energy. So the change in energy of the system is a change in internal energy. So the work in is causing an internal energy change. It's interesting. Everything depends on where the boundary is drawn. What if I change it up? You see what just happened as I increase the slide? Look at the boundary here, right? The boundary includes the heating element. Now, I am going to redraw my boundary. Let me go ahead and erase this so it's a little more clear. I'm going to redraw my boundary so that now the boundary is around the heating element, and the heating element is outside the system. Now the electric work's being converted into increasing the temperature of the heating element, and that results in heat traveling across the boundary into the oven. So now there is heat transfer, right? Slight change in how I define my boundary, which completely changes how I quantify my energy terms. So in this scenario, I would have Q going in, causing a change in internal energy. So the moral of the story is it's very important to know where you define your boundaries. All right. Next slide. We're going to end this video on this slide, which is looking at electrical work. In an electric field, electrons in a wire move under the effect of electromotive forces. So when I look at electric power, I define that, or I quantify that by current times voltage, right? Or the amount of work that occurred electrically is equal to the voltage times the charge quantity. So I have here, this should be a subscript E there. This is electric work, right? Electric work, where the electric work per time, that's defined as electric power. V is voltage. N would be charge quantity. And finally, I would be current. Okay, I think this is a good point to stop. So we will continue with the rest of the chapter, with more of the chapter in the subsequent video. Thank you.